Hello, I'll be talking about experiment 4, varying training sample size. Now, before I get started, let me introduce you to the best 3 performing models from our previous 3 experiments, right? Namely experiment 1, 2, and 3, with the following algorithms and parameters that we'll be using for experiment 4. Varying training sample size. Now, typically, we will split our dataset into test, development, and training sets as follows. However, for the purpose of this experiment, the training dataset will be further divided into 10 equal subsets as described here. Now, we will then incrementally feed each subset by subset into the machine learning algorithm and record the results accordingly. We will repeat these steps for each of the best performing machine learning algorithm from experiment 1, 2, and 3. The purpose of doing this is basically to test that if increasing the sample size of the training sets, would it improve our performance model? Since we never done such splitting of the training dataset into subsets before, a small validation was done using sklearn train test split function with incremental split ratios as described. Based on the result, we can conclude that sklearn train test split function was able to meet our experiment expectation requirement, provided we fix the random state value to ensure we get a reproducible result. Based on the experiment results, here are our findings. Starting with experiment 1 best performing model, we find that as the training sample size increases, so does the training accuracy. However, you can see that it starts to decline after 60% of the training sample size. For the test accuracy scores, there is some variation at less than 50%. However, it's generally flat across the range. For experiment 2 best performing model, since the classifier and parameters are exactly the same with experiment 1, only with the non-significant feature height being removed, we find their result to be very similar. For experiment 3 best performing models, it shows similar response on the training data set accuracy, and the test accuracy score is relatively flat as well. Looking at the test accuracy statistics in detail, we find that the standard deviation for all 3 models to be very low. Now, this correlates to our findings that increasing the training sample size did not show any significant improvement to the best performing model's prediction accuracy for our dataset. So, in summary, for experiment 4, doing a simple validation, we were able to prove that sklearn train test split function is able to model experiment requirement, provided we fix on the random state value. With incremental training sample size, there is a general correlation that more training sample improves the training accuracy. However, there's an inflection point where the training accuracy declines. This is possibly because more noise was introduced in the dataset, causing our simple machine learning algorithm, while able to model with high accuracy with a low sample set, but find it difficult when more noise was introduced. Based on the test accuracy score, increasing training sample size did not demonstrate any significant influence for our dataset. The machine learning algorithm used logistic regression may be too simple and was not able to explain our data well. Now, we could potentially improve on the model by using a more complex nonlinear machine algorithm like support vector machine or neural network, right, to overcome our high bias model potentially, right? But that's another discussion for another project. So for now, that's the end of my presentation for experiment 4. Bye bye.